So let's look at the net change theorem. The integral of the rate of change, or this big function, f prime of x, is going to be equal to the net change, or our function at our b value subtracted from our function at our a value. This concept is fairly simple, but it's very vital to calculus and to solving complex integrals. Let's look at a few simple examples first, and then we can go on to a more complex real-life situation. So we have an integral going from 0 to pi of 5e to the x plus 3 sine x dx. So let's break our terms into two pieces just to make it a little bit easier. So I have 5e to the x and 3 sine x. All right. So let's take the integral of both of these, and then we can combine it into 1. So if we integrate 5e to the x, we know 5 will stay the same, and so will e to the x. Integral of e to the x is just e to the x. So 5e to the x for our first term, and then 3 sine x. Well, we know the 3 is going to stay the same, but what about the integral of sine x? Don't get it confused with the derivative and say cosine x. Remember that it's integral, so it's opposite. It has to be negative cosine x. So the integral for that term is going to be negative 3 cosine x. And then let's just make some room so we can write everything all down nicely. So if we use the net change theorem, which is, again, integral going from a to b of our rate of change function is equal to the function's integral of b minus a. So now we could just follow this pattern. So for our example, our b value is going to be our pi, and our a value is going to be our 0. So if we have f of pi, we'll have 5e to the pi minus 3 cosine pi. And then, again, just following the net change, we'll have minus, in parentheses, we'll have 5e to the 0 minus 3 cosine 0. And from here, we can just simplify. So we know 5e to the pi, that's just a constant, so we'll leave it as it is, 5e to the pi. Since we don't want any decimal approximations in our answer, we want exact answers. And for our cosine pi and cosine 0, let's actually draw our graph of cosine and determine which values that we have. So right here is 0. We have pi over 2 at this line. Over here we have pi. And then our third mark will be 3 pi over 2. And then our last one, back at 1, will be 2 pi. So we have minus 3. Cosine of pi is negative 1. So we'll have 3 times negative 1 minus 5e to the 0. E to the 0 is just 1. So we'll have 5 times 1 minus 3, and cosine 0 is 1. So just 1. When we simplify this, we'll have 5e to the pi plus 3 minus 5 minus 3 is 2. And then our last step is combining like terms. 5e to the pi stays the same. 3 minus 2 is positive 1. So 5e to the pi plus 1 is our net change of our integral. So let's take a look at another example. We'll have 0 to pi over 4 of 1 plus cosine squared theta over cosine squared theta d theta. Now, the first steps to this is to manipulate it algebraically. So if you can see any terms might cancel or just make it easier to integrate. So this 1 plus cosine squared theta over cosine squared theta can be rewritten as 1 plus 1 over cosine squared theta. You can see that this actually works because 1 can just be represented as cosine squared theta over cosine squared theta. And then if we have plus 1 over cosine squared theta, we can just see if we combine like terms in the denominators, we'll be left off with cosine squared theta plus 1 over cosine squared theta, which was the same thing that we had in our original integral. Our next step would be to recognize that our 1 over cosine squared theta can be written as secant squared theta, d theta. And now if you know your basic integrals, secant squared theta is just going to become tangent theta. So that's why we had to manipulate it, so it can just become a simple integral. So we have our two pieces, 1 and secant squared theta. Let's find their integrals. So we know that any constant that is integrated with respect to a variable is going to become that variable. So 1 is just going to become theta when we integrate it because we're integrating with respects to theta. And then as I said earlier, secant squared theta is one of those basic integrals that you should remember, and that just turns into tangent theta. So we have our two pieces, theta and tangent theta. And that is our function when we're using the net change theorem that we want to plug in our values in. So again, using the net change, a to b, of our rate of change is going to be equal to f of b minus f of a. So if we just plug that into our integrals that we got before, we'll have pi over 4 plus tangent of pi over 4 minus 0 plus tangent of 0. And now from here, we can just simplify and find our answer. So pi over 4, that stays the same because it's a constant. And then for our tangent of pi over 4, let's draw a special triangle, our 45, 45, 90 triangle. So if we do that, we know our sides are going to be equal to 1, 1, and then our hypotenuse is square root 2. We know that tangent is the relationship between the opposite side of our angle and the adjacent side of our angle. So if we have tangent of our 45, 45, 90, or pi over 4, we can see that our opposite angle is going to be 1, and our adjacent is 1. And 1 over 1 is equal to 1. So we'll have pi over 4 plus 1 minus 0, and then tangent of 0 is 0 as well. If you don't have an angle, you won't have any sides. So then our final solution is just pi over 4 plus 1. We can leave it like this, but if we use the same trick on our 1 that we used to break up our integral in the first step, we'll be left off with 4 plus pi over 4. And that is our final solution. So now for our real-life application. The velocity of a particle in meters per second is given by the function v of t is equal to 3t minus 5. Find the displacement of the particle on the interval 0 to 3. So we know that a velocity is actually a rate of change function. So that's what's telling us to use the net change theorem, because the net change theorem deals with rate of changes. So let's just set up our integral going from 0 to 3, and then our function of 3t minus 5 dt. Okay, so just like before, let's break our pieces into two different sections. We'll have 3t and negative 5. The integral of 3t, using the power rule, it's going to be t and then 1 plus 1, since our starting power is 1, over 1 plus 1. And then don't forget our constant on the outside. So 1 plus 1 is 2, so we'll have 3t squared. And then 1 plus 1 on the denominator, again, is 2. For our negative 5, again, our constant when we're integrating it with respect to a variable is going to be that constant times that variable. So we'll have negative 5 times t. And then it's just negative 5t since we're integrating with respect to t. So now that we have our integrals, we can use the net change theorem, remember f of b minus f of a, to get our total displacement, to find our answer. So we'll have 3 times 3 squared over 2 minus 5 times 3 minus 3 times 0 squared over 2 minus 5 times 0. So starting on the right side, 0 squared is going to become 0. 0 times 3 is 0. 0 divided by 2 is 0. And then minus 5 times 0 is 0. So everything just becomes 0 on the right-hand side. Pretty simple. All right. Now for our left side, 3 squared is 9. So we'll have 3 times 9 over 2 minus 15. 3 times 9 is 27. So 27 halves minus 15 minus 0. And then finally, if we just simplify, we'll receive negative 3 halves. And then m for meters. And so let's try to interpret this answer. Is it correct? Is it not? It's a negative. What does that mean? So we were asked for displacement, not total distance. So we know our displacement can be negative. So that just means our particle, whatever path it went along, it ended further than the point where it started. And in our case, it ended up 3 halves meters away from where it started. So that's why our answer is negative, but it's okay to have a negative displacement.